Hey everybody, thanks for checking in today. In this lesson we're going to look at how to calculate higher order derivatives. So not just a first derivative, not just a derivative, but talking about a second derivative or third derivative or anything after that. Okay, let's start with talking about something that we're going to talk about a lot moving forward here. The position of an object. All right. So you can see in this little table here, if we have the position of an object given by a function as s of t, the first derivative of that, so s prime of t, is going to give you the velocity of that object at any time. However, if we continue and take the second derivative of s, so s double prime of t, that will give us the acceleration at any time. So this is why it's really important to be able to take higher order derivatives, because when we're talking about positions of objects, we want to know its acceleration often. Okay? So here are some ways we would write that. Okay, if we want to take the first derivative, we know that as y prime or f prime of x or dy dx, right? But we can also take more derivatives than just one. So the second derivative would be y double prime or f double prime of x or d squared y over dx squared. Third derivative can be written like these. Anything higher than a third derivative, though, we don't want to keep putting tick marks. Imagine trying to take a 50th derivative and you're doing y with 50 tick marks there. So if it's higher than a third derivative, what we do is we just do y parentheses 4 or f parentheses 4 of x. Okay? Why the parentheses? Because if we just wrote this, you might think of that as y to the fourth. So if we put parentheses around it, that means the fourth derivative. Okay? So anything higher than 3, like I said, so anything to the nth power, that's how we'll write it. All right, so why does the notation for the second derivative look like that, or third derivative, or fourth derivative? Think of it as taking the derivative of the first derivative, or this. The notation above, we can condense down to that form there. Okay, and that's the same for third derivative, fourth derivative, or anything higher than first derivative. So a real basic problem here to start off with. The question says find the second derivative. Well, you can't do the second derivative without doing the first derivative. So let's take the first derivative of this, and we get 6x squared plus sine plus 1 over x minus e to the x. And that's our first derivative, and that's where we've stopped up until this point. If I want a second derivative, I'm just going to take the derivative of the first derivative. So that'd be 12x plus cosine 1 over x, remember that as x to the negative 1, so that's negative 1 x to the negative 2, or negative 1 over x squared minus e to the x. And that's it. That's our second derivative. And then we could keep going and take a third and fourth and fifth if we wanted to. But that's where we're going to stop for example 1. All right, back in chapter 1, we talked about this Burj Khalifa building and a couple examples. We're going to revisit this scenario right now. Suppose a ball is dropped from the top story. And don't try this at home, kids. A ball is dropped from the top story of this building 2,717 feet above ground. The position equation that depicts the height s of t in feet, the ball is from the ground at any time t, is modeled by this equation here. S of t equals negative 16t squared minus 10t plus 2717. Obviously, the 2717 being the initial height of the ball. So A says compute the velocity of the ball at t equals 5. So we need the velocity equation, which remember is the derivative of the position equation. So that would be negative 32t minus 10. So if we want to find v of 5, we just put a 5 in there, and we get negative 170 feet per second. How do we know it's feet per second? Feet and second. B says compute the acceleration. Okay, well now we need to take the derivative of the velocity. The derivative of the velocity is your acceleration, and that's just negative 32. So the acceleration at any time, specifically at 5, would be negative 32 feet per second, or feet per second squared. When will the ball hit the ground? All right, so that means when will the height be 0? In other words, when will the position function be 0? So we're going to set s of t equal to 0. And we're not going to solve this mathematically. You could definitely use the quadratic formula to solve this, but it'd be much easier to just take this equation here, put this into y1, and find the zeros using your calculator, okay? If we do this correctly, we should get a picture that looks probably something like this. All right, it's kind of like half a parabola maybe. And if you can find the zeros in the calculator, you're going to get t is approximately 12.723 seconds. So then D says, what is the velocity of the ball when it hits the ground? Not after, because obviously after would be 0. But we're going to take this velocity equation, and we're going to place 12.723 in for t. And again, we can use our calculator to help with this. It would be negative 417.12 feet per second. All right, example 3 says, because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon, even though the hammer is obviously much heavier. The position function for each of these falling objects is given by s of t below, where s of t is in meters and t is in seconds. What is the ratio of the Earth's gravitational force to the moon's gravitational force? Okay, so on Earth, we know that there's a position function out there that you probably have learned in your physics classes. The acceleration on Earth is negative 9.8 meters per second. Okay, so if we build up from that, we have this position function on Earth that we're going to use as negative 4.9 t squared plus the height, starting height, which we can see here, is 2. All right, so this is on Earth now. So our derivative of that will be our velocity, which is negative 9.8 t plus 0. And our acceleration is just negative 9.8. Now on the moon, the position function is given right here. All right, now our velocity would be negative 1.62 t, and our acceleration would be negative 1.62. So the question asks, what's the ratio between them? So the ratio of Earth to the ratio of the moon gravitational pull, you can put that into your calculator as well. It's going to give us a number that's a little bit bigger than 6.049. What does that mean? That means that the Earth's gravitational pull is about 6 times as strong as that of the moon. All right, here's a little bit of a challenge. So a challenging second derivative. Just like before, to do a second derivative, we got to do a first derivative. So remember, the derivative of the cosecant of a function is the negative cosecant cotangent of t. So to find the second derivative, and maybe this isn't as challenging as I said here, but really all we got to do is we got to use the product rule on this. So kind of think of as this as your first function and this as your second function. So we have the first function times the derivative of cotangent, which is negative cosecant squared, plus the second function times the derivative of the first function, which is negative cosecant, so cosecant cotangent. And that's it although we can definitely clean this up a little bit. This would be cosecant cubed plus cosecant cotangent squared. And if it was a multiple choice question, maybe we could take a cosecant out of that, take a cosecant squared plus cotangent squared. So it'd be cosecant times cosecant squared plus cotangent squared. But this would also be good enough for an answer to a written question here. In fact, this would be good enough for an answer for a written question. All right, so here we have 3 practice problems that you should probably at this point pause the video and try to figure these out on your own. And when you're done with all 3, come back and unpause the video and check your answers. All right, here are the 3 answers. Feel free to pause the video and take a look at this as long as you need for help. And to wrap up today, we're going to do one more problem. This is called, as we've already done in the past, implicit differentiation. So here's an example of an equation that we probably want to do the derivative implicitly. And I'm going to say, let's find the second derivative of this. All right, so the first derivative is just 2x times dx dx, which is 1, plus 2y times dy dx equals 0. All right, so to solve this for dy dx, I'm going to subtract the 2x over and divide by 2y. And I get negative 2x over 2y, or just negative x over y. And that's our first derivative, right? Now to do the second derivative, we're going to have to use the quotient rule on that. So to do the second derivative, we're going to have to choose here. I'm going to choose to let the negative go with the x. You can choose to let the negative go to the y. It doesn't matter. I'm going to have the negative go with the x. So it's going to be denominator times derivative of the numerator minus numerator times derivative of the denominator all over denominator squared. All right, if we simplify that a little bit, we get negative y plus x. Now, for dy dx, we know what dy dx is. It's negative x over y. So put that right in there. Over y squared. Simplifying a little bit more here, negative y, and then we have minus x squared over y, all over y squared. Kind of running out of room here. All right, now up here, if I get a common denominator, I'm going to multiply this term by y over y, and that would give me negative y squared minus x squared over y squared, which I can then simplify down to negative y squared minus x squared over y cubed. And that would be our simplified second derivative. All right, and that is it for today. Thanks again for checking out this video. I hope you enjoyed higher order derivatives, and we will see you again soon.